to be here remotely. Appreciate that. And I'd like to thank Janet, who's been very influential, particularly in encouraging me to go see the David Fields talk, which was seeded a lot of this work.
I remember that.
So I'd like to thank the NPCR lab members, in particular Stephanie Lukowicz. She's been an incredible help. This would have, again, never happened without her help and support. Dan, obviously just the same, tremendous help with the research. Mike Teddy as well with LCA. Chad, Mike, Junior, Washington, Carson, Paul, Sean, Nicholas, Marcus, Andrew, and the rest of them won't fit. Special thanks to my Internet Dream Team. There's a lot of generous people who make their work open source. Thankfully, they're tenured professors. They don't have to worry about keeping their things secret, and they're generously provided their slides on the Internet. So a lot of this work is developed from those folks. So I'd very much like to thank you for your time today. I truly appreciate your attention, and if you have any questions, I'd love to answer them. Thank you.
Forget, does the committee go first?
Yes.
Okay, so questions from the committee. Howard, since you're remote, why don't I start with you? Let me crank them up a bit. We're at committee question time, so you're first.
Thanks a lot. I really am a little overwhelmed. I can't think of any intelligent questions to ask. Do you think some of these approaches will be useful to more specifically tie to behavioral results?
Yeah, I think the things that I'm excited about in terms of the next steps would be the motion perception. And I know, Howard, to tie this into what you do, to look at these features, particularly with the video paper, that it had to learn something. It had to learn something about shapes and then how those shapes move. And so does that model, or in any way can we combine that or look at that in terms of motion detectors? Do we have receptive fields in MT, let's say, that are looking for particular types of motion, biologically relevant motion? And so I think there's a lot of good work to be done in terms of that front.
Do you think the nodes, the hidden nodes in the model will reflect different kinds of receptor fields, including some that we don't know about? I
think that would be the most exciting if we found something we didn't know yet and then could then find it. I mean, that's sort of the classic scientific goal. But yeah, I think, we had talked briefly, subject motion and object motion. Would these things fall out? If you had noise, if you had, maybe even a saccade, you could fake. You can get webcams now that tilt and pan. I thought it'd be neat to make one of those that have to actually pan and tilt around the world. But to see what sort of features it learned, and are those things anything like the features you'd find in biology? That, are animals employing a similar type of system to detect motion?
Well, I look forward to that enterprise.
George?
That's all I have for now.
Thank you.
A quick question about the image reconstructions for MRI. I would say for CT maybe it's a little bit easier. So each slice is giving you a sinogram, right? So for each slice you have one sinogram. So do you believe you can apply this Sparse modeling to reduce the projections? But
yeah.
Each person is different. For instance, you can say maybe for head or maybe for pelvis, it would be possible.
I think so. I think definitely having a dictionary specific to the different regions would be very helpful,
yeah,
right? So that something could know, oh, I'm reconstructing a jawbone, so then that can bring in some dictionary specifically for that and help.
The whole head.
Yeah, for the whole head, right? I mean, that would be ideal, is if the computer could then identify what those regions are, particularly if you didn't tell it.
I mean, if you want to do like the head, you can easily say, okay, I want to classify like head, pelvis, lung, and so forth. So it might be helpful somehow to classify it. Right?
Yeah, I think that would be really extraordinary if you could just give it a raw scan and it would sort of just color code it. Put different organs of different colors and type thing. They would have an idea of what we were talking about the textures. And so if maybe from the texture itself, it could say, oh, this is liver texture or this is heart texture.
Excuse me. So The plausibility of compressed sensing is sort of being biological. You mentioned the digital camera takes many pixels that it then throws away. The compressed sensing is in a certain sense meant to avoid that step, but our optical system, in fact, does do very much does that. There are 100 million photoreceptors per eye, about 2 million ganglions by the time the optic nerve. So it seems, at least in the eye, that we aren't using compressed sensing. Why wouldn't evolution have perhaps arrived at this solution?
Yeah, it's a great point, and I would certainly think that it's not happening everywhere. And in some parts of the visual system, it's going to be important to keep that information. Like, where in the scene was the tiger? It was like up in this corner of my vision. And so in that sense, you don't want to sort of throw everything away. And so it probably is that the compressed sensing is being learned on the later in the system. I would argue that something like LCA is happening on the front end, and then on the back end is the compressed sensing. And so I would think that the feature detection is happening with these dictionary elements. But then once you can detect certain features or certain properties of your input, you're then going to have to build like a reinforcement learning model. And I would think that the compressed sensing is going to be showing up later. And then in a sense, a lot of times when we have like a decision we make and we say, well, it's like a gut decision, we can't verbalize it. It's hard for us to reverse how it is that we made that decision. And that might be like this, that we can make inferences without doing reconstructions. And so for the visual system, a lot of times we probably need the reconstruction and we need the place, the localization of things. But for other things like making judgments and value estimations, we might not have to have that. So to kind of answer your question, I would think that compressed sensing is showing up later in the game, in the behavior recommendation. And that the front end is going to be using these compressed sensing. But it's probably going to be using both at the same time as well. You can imagine, and I think there's interesting questions with development here too. We were discussing yesterday, I mean, when I was young, I was very intrigued by the fact that my mother, for example, could remember something 20 years before with no problem. But when I was 7, I couldn't remember being 2. And so that didn't make sense to me, how you don't get your memory archive system doesn't come online until you're like 2 or 3. And so I would make the argument that you have to learn a dictionary first. That when you're born, you can make decisions and things. You can do stuff. You can learn contingencies and reinforcements. But you can't build the sort of model-based understanding of the world we have because you don't have that dictionary yet. And so obviously this is very speculative, but it'd be very interesting to look and see that if in development you're building these dictionaries, and then once they get rich enough, then you can sort of save those memories. Does that kind of answer some of it?
I guess we open to the rest of the audience. Questions?
Are you familiar with the concept of an adverse example?
Adverse example? Yeah, so it's not something we study. I can assume something of what you mean. So these neural networks, you have them classify certain objects. And from what I understand, there's certain things you can show to try to trick them.
Yes.
Is this what you mean by?
So an adverse example is, say, the picture of a cat, in which a small amount of pixels have been randomly changed. The human eye or the human will not make any difference. It will still recognize the same cat, and actually it will make no difference in the picture. Yet the neural network, the deep learning algorithm, will misclassify that picture. Yeah? So, in the context of this compressed coding, where you are multiplying with a random matrix, it seems that this kind of error seems very probable in your system. Have you tried to address this?
So we didn't try, and we didn't have any adversaries in our model per se. It's very interesting, yeah, to think about the noise for the compressed sensing. With the compressed sensing, you still have to take many samples, and so you're still going to take thousands of these samples. It's less than the millions you would have taken. So in that sense, I think it's not quite with adding the noise to the adversarial, but it is very interesting that you have these pictures, like you said, and it can be a picture of a dog, a cat, and then you add to it something that's just noise. I mean, you add like confetti to it, is what you're saying, right? It's very surprising result. So this is with a convolutional neural network. So this is with a different architecture. But with the convolutional neural network, you do have this problem that and again, you have to very carefully calculate that noise. You can't just make noise and add it, but you can, by knowing what this thing likes, you can screw with it in a very particular way using calculus and get it to switch its definition. It'll say that's a dog now. And so not only will this picture still look like this picture, a human won't even be able to tell these apart. So it's very strange, but that's a problem with the convolutional neural network. So we haven't tried it with this, but it's a very good question to see if this is subject to that. I would hope and argue that it's not, but we don't know.
If you will have to speculate, what do you think that in human brain is implemented as a dictionary overview that prevents us from making this mistake?
Probably context. Probably just the sort of the larger scale statistics of, oh, I'm in a room, I'm with people, and it's the afternoon, and that in a confused state, you might get just that. And certain people might switch those categories. It'd be really interesting to look at the psychophysics in that to see if there's something analogous. Can you get people to report the thing? But I haven't heard of anything like that. But again, it's neat that this image that you've changed it in a way that a human could never tell the difference, but you've got the computer to think it's something completely different. So we haven't looked at that with this, so that's a very good idea to try. Yes.
More of a comment. I think that there's some argument about perception being influenced by anticipation, context, memory. And it just makes me, as I was listening to your talk, I was thinking that maybe compressed sensing is that drive of attention. Have you given much thought to that?
So
it's a way of saving energy.
Yeah, definitely. Particularly, you can imagine if you're bringing in these, can I use a few of them from the time before, kind of thing. So one of the things that is exciting about LCA is that you can do updating on it. And so that if you give it something new to code, it can start with the thing it was coding last. And so if you're giving it movie frames, it'll code that frame, and then you give it the next frame. It's very similar. And LCA, unlike the others, it doesn't have to start from the beginning. It starts with what it was just doing and then just makes a few changes. And so that could model anticipation in a sense, that you've got sort of it primed, and you've got a code sort of ready, even though it's not even in the input yet. It's sort of being anticipated that that's going to be needed next. So I think, but it's a very good question to sort of know what that code is next, right? So you have the code coming in, and you want to know what's the next code going to be. And with the compressed sensing, it could be cheaper to predict the next compressed code than to predict the whole scene, maybe.
You told us at the beginning that you were going to tell us about how the brain works, right?
Right.
And then you showed us all those dictionaries, the dictionary for the monarch butterfly and butterfly and this and that. One missing thing here is we have, you oriented us, you said, look at this region, there's that particular properties. So how do you connect those dictionaries, I don't like the fact that they are plural, to the commonality of human experience, which is inscribed in the neuroanatomy and the functional organization of the visual cortex? What's missing for you to go from those dictionaries to the singular dictionary, which represents the overall human perception?
Right. Exactly. It's not going to be, the idea that there's an image dictionary and then a sound dictionary doesn't make any sense. And so, in general, it's going to be one dictionary in the sense that the neurons wouldn't even know which inputs came from vision and which came from audio, and if they're all mixed together, and if maybe this is the muscle and it's in your position that you're in, and maybe it's the mood and what your tummy's doing, and all of these would sort of get added in to this big mess, and then it has to code that's going to be this messy dictionary. And I think this is why it's so hard to go in and find stuff with electrophysiology, because the dictionaries are so multimodal. They're going to be responding to almost everything that their neighbors are. And so I think this is a really good point, and that ultimately we want, right, again, my apologies because this is the opposite of the brain, but just to tease our little this little guy, right? You know, if we want him to pretend at least like he has a brain, that we cannot have an image dictionary and then an audio dictionary and then some laser dictionary. It's going to have to be all together, and then it's going to have to make reinforcement learning on top of that.
So even if you think that it's only the visual system for simplifications, would you say that your failure to capture something general in all those cases has something to do with the too short and too specific ontogeny of those neural networks that you create for specific applications?
Yeah, I mean, in the sense that you've already determined so much by making it about little patches and then making it about pixels and things. I mean, if I can understand what you're getting at is that you've already assumed a lot by assuming this type of framework. Is that what you're asking?
That's one aspect of this, but that's not the only one, I think. So how do you get from those dictionaries to something that tells us, oh, that's exactly the same than what we find in the visual systems, for instance?
And so, well, that comes from these model fits. And so what they'll do is they'll actually take the electrophysiology data and then they'll do a simple model fit on it to see what it is that this receptive field is trying to find. And when that's done, it's loading. So what you'll see here in a second when this loads up is we have up top the actual visual cortex. So this is a model fit to a cat. And so we can see that at first they said, well, these just look like Gabor functions. And so psychophysicists for a long time, that's their bread and butter, is just look at Gabors. They put them on the monitors and different angles and see what people can see. But then sort of the new layer of things is, oh, it's not just a coincidence that they're Gabors, that these are really sparse filters. And that when you go and you record from actual neurons that they look like this, and then the sparse modeling framework comes up with this, and so this is evidence that the receptive fields are attempting to sparse model their input. Yeah?
Maybe part of this is that the Andrew Cowler layer political architecture. Maybe you could talk about that, because I think they died.
Yeah,